Right now, as you watch this orbiting the planet Mars at nearly 22,000 kilometers per hour, there is a dead spacecraft. It has no power, no signal, no one listening to it. Its solar panels are frozen at the wrong angle, its thrusters fired for the last time over 2 years ago. And somewhere inside its silent body, 5 scientific instruments sit in the dark, including one that was supposed to answer the single most important question in the history of human civilization. Is there life on Mars? That instrument never worked. And for years, no one in India's space agency said a word about it. But that's not even the strangest part of this story. The strangest part is this. Mangalyaan, India's first Mars mission, spent 8 years orbiting the red planet. It completed over 7,000 laps around Mars. It transmitted 2 full terabytes of data back to Earth. 32 separate research teams were assigned to study that data. And after all of that, after 8 years, 2 terabytes, 32 teams, only 27 research papers were published. 27. NASA's Maven spacecraft went to Mars the exact same year. It published over 500 papers. So here is the question that nobody in mainstream science media has fully answered. What is inside those 2 terabytes? What did Mangalyaan actually find on Mars? And why has almost none of it ever been made public? To understand what happened, we have to go back not just to the launch, not just to 2013, but to a church, a bicycle, and a bullock cart. The 21st of November 1963. The village of Thumba in the southern Indian state of Kerala. There is a small whitewashed church here, Street Mary Magdalene, and inside it, instead of pews, there are drafting tables, soldering irons, and rocket components. Outside, leaning against the church wall, a bicycle is parked. Tied to its frame, bungee corded to the handlebars, is the nose cone of a rocket about as long as a tall man. A bullock cart idles in the dirt road nearby. Strapped to its wooden flatbed is the rocket's body section. 2 scientists in white shirts walk alongside it, carrying notebooks, checking their watches. This is India's space program on day 1. No launch pad, no countdown room, no billion-dollar budget. Just a church that the local bishop agreed to vacate, a handful of scientists who had been trained abroad and come home to build something from nothing, and a rocket so small it would look like a firecracker next to what we launched today. That rocket, the Nike Apache-sounding rockets, launched from a sand beach near the Arabian Sea. After it flew, the scientists sat under a coconut tree and analyzed their data by hand. That was mission control. Now hold that image in your mind. Because the same organization, ISRO, the Indian Space Research Organization, is the one that, 50 years later, designed, built, launched, guided, and successfully inserted a spacecraft into Martian orbit on a budget of 450 crore rupees. That's roughly 74 million US dollars. For context, the Hollywood film Gravity, a movie about space, not an actual space mission, cost more than that to make. And NASA's Maven mission, which launched the same year as Mangalyaan, cost the equivalent of nearly 5,000 crore rupees, almost 11 times more. So when India announced in 2013 that it was sending a spacecraft to Mars, much of the Western world laughed. There were memes. Newspaper cartoons showed a turbaned man riding a rocket like a bicycle. Western media called it India's auto rickshaw to Mars. The scientists at ISRO said nothing. They went back to work. Because they knew something the mockery missed entirely. The engineering problem they were solving wasn't just about reaching Mars. It was about reaching Mars within the constraints of what India actually had: a medium-lift rocket that wasn't powerful enough for a direct trajectory, a budget that didn't allow for a single mistake, and a team that was, by global standards, very small. And they solved it. Brilliantly, ingeniously, with a technique that deserves far more attention than it gets. But the real story, the uncomfortable story, starts after the launch, the 5th of November 2013. Sriharikota, Andhra Pradesh. The PSLV C-25 rocket stands on the launch pad like a white tower in the morning haze. Inside its payload fairing, the protective nose cone at the top, is Mangalyaan. The spacecraft weighs 1,337 kilograms. It carries 5 scientific instruments, and one of those 5 instruments is, without question, the most significant payload that ISRO has ever flown. Its name is the Methane Sensor for Mars MSM. Here's why that matters. On Earth, roughly 90% of all atmospheric methane is produced by living organisms, bacteria, livestock, decaying organic matter. Methane is, in the most literal sense, the gas of life. It is a biosignature, a chemical fingerprint that says, something alive was here, or still is. Scientists have suspected for decades that if Mars harbors life, even microbial life, buried kilometers deep beneath the radiation-blasted surface, it would likely produce trace amounts of methane. The gas would seep upward, accumulate in pockets, and eventually reach the thin Martian atmosphere. So detecting methane on Mars would not just be an interesting data point, it would be, and this is not an exaggeration, the most important discovery in the entire history of science. It would mean we are not alone. Mangalaan's methane sensor was reportedly sensitive enough to detect even 1 part per billion of methane in the Martian atmosphere. That is extraordinary precision. That is the kind of instrument you'd expect to cause a global sensation the moment it started returning data. The rocket launched, the mission entered Earth orbit. Over 25 days, ISRO's team fired the engine 6 times, each burn expanding the orbit a little wider, the same way you'd spin a stone on a string and gradually let it out. On the 1st of December 2013, the final burn fired. Mangalyaan broke free of Earth's gravity and began its long fall toward Mars, 680 million kilometers, through absolute darkness, alone, with no way to call for help. It had 9 months to travel, and the world waited. The engineering miracle nobody talks about. What happened between December 2013 and September 2014 is, in purely engineering terms, one of the great achievements in the history of spaceflight. Think about what Mangalyaan was doing. It was navigating through interplanetary space using pre-programmed instructions loaded before launch. It could not receive real-time course corrections. The signal delay between Earth and Mars is over 12 minutes each way. By the time ISRO noticed a problem and sent a command, nearly half an hour would have passed. The spacecraft had to be, in a meaningful sense, smart enough to save itself. And on the 24th of September 2014, it arrived. The moment of truth was called Mars Orbit Insertion (MOI). The spacecraft had to fire its main engine at exactly the right moment, for exactly the right duration, to slow down just enough for Mars's gravity to capture it. Too fast, and Mangalyaan would shoot past Mars and drift into deep space forever. Too slow, and it would fall toward the Martian surface and burn up in the thin atmosphere. There was no room for error. And crucially, for those final 24 minutes of the burn, Mangalyaan was on the complete far side of Mars, invisible to Earth, unreachable, making the decisions on its own. ISRO's mission control in Bengaluru went completely quiet. Prime Minister Narendra Modi was in the room. Scientists stared at screens showing only the trajectory prediction numbers and curves, nothing more. And then the signal came back. Mangalyaan had done it. First attempt, Mars orbit achieved. India became the 4th entity in history after the United States, Russia, and the European Union to successfully reach Mars, and the only one to do it on the first try. The scientists wept. The Prime Minister shook hands. Around the world, the mockery evaporated overnight. But here's what nobody was paying attention to in that moment of triumph. The spacecraft's most important instrument had already been switched on during the cruise phase. The methane sensor had been tested, and something was very wrong, but no one was saying so yet. Mangalyaan settled into its elliptical orbit around Mars and began working. The Mars color camera was extraordinary. It returned images of the Martian surface in stunning detail: the ochre deserts, the enormous impact craters, the polar ice caps frosted white against the red plains, dust storms spiraling upward like slow-motion catastrophes. From these images alone, ISRO assembled one of the most complete photographic maps of Mars ever produced from orbit. Another instrument, MENCA, the Mars Exospheric Neutral Composition Analyzer, found something genuinely puzzling in the upper layers of the Martian atmosphere. Argon atoms were moving faster than they should have been at that temperature. Something was giving them extra energy, something that existing models of the Martian atmosphere didn't fully account for. It was a real, interesting, unexplained finding. And the Lyman alpha photometer was measuring how quickly Mars was losing its water, watching the hydrogen atoms escape from the thin atmosphere into space, helping scientists understand how Mars transformed from a wet, warm world billions of years ago into the frozen desert it is today. These were not nothing. These were legitimate scientific results from a spacecraft that cost less than a mid-budget Hollywood film. But the methane sensor? Silence. 6 months passed. No press conference about methane, no preliminary data. No, we're still processing, just nothing. 1 year passed. The international planetary science community began asking questions, politely at first. ISRO said little. 2 years passed. The questions became less polite. And then, in 2016, a senior NASA scientist named Michael Muma said it publicly at a scientific conference. The Mangalyaan methane sensor, he explained, had a fundamental design flaw. When it measured the Martian atmosphere, the signals from methane and carbon dioxide, which makes up 95% of Mars's air, were overlapping. The sensor couldn't separate one from the other. It couldn't tell you how much methane was present because it couldn't distinguish methane from the noise of the carbon dioxide all around it. The instrument that was supposed to detect alien life was, functionally, blind. ISRO's response? No press conference, no correction, no explanation offered to the public. They quietly renamed the instrument. The methane sensor for Mars became, in official documents, a reflectance spectrometer, a device for measuring how much sunlight bounces off the Martian surface. The instrument that crossed 680 million kilometers to find life was now, officially, counting light. That silence, that particular deliberate quiet, is where this story gets genuinely uncomfortable. So what did Mangalyaan do after that? It kept going. The mission had been planned for 6 months. Mangalyaan lasted 8 years. By the time it fell silent in 2022, the spacecraft had completed over 7,000 orbits of Mars. It had transmitted back to Earth approximately 2 terabytes of scientific data. To understand what that volume means, if you printed 2 terabytes of text on standard A4 paper, you'd need hundreds of millions of sheets. That's not a footnote, that's a library. In 2017, ISRO announced that 32 separate research teams across India had been given access to this data. 32 teams. Scientists at universities and research institutions across the country, given the raw output of 8 years of Martian science. So, how many peer-reviewed papers came out of it? 27 in 8 years. From 2 terabytes of data, with 32 teams working, 27 papers. And of those 27, more than half are engineering papers describing how the rocket launched, how the orbit was achieved, how the instruments were calibrated. Valuable documentation, certainly, but not planetary science. Not the kind of discovery papers that change what we know about Mars. Meanwhile, NASA's MAVEN, the Mars Atmosphere and Volatile Evolution spacecraft, launched within weeks of Mangalyaan, arriving within days of it, published over 500 papers from the same time period. 500 against 27. That is not a small difference. That is a 15-to-1 gap. That is the difference between a mission that reshaped our understanding of the Martian atmosphere and a mission whose scientific legacy remains, in large part, locked inside hard drives that the public cannot access. And it gets more specific than just the methane sensor. The Lyman alpha photometer, the instrument measuring Mars's water loss, never had its primary scientific results formally published. The data exists. ISRO confirmed it exists. Scientists were invited to use it, but the papers haven't come. Why? The honest answer is, we don't fully know. And that uncertainty is itself a kind of answer. April 2022. Mars is currently on the far side of its orbit from Earth, 225 million kilometers away. Mangalyaan is running on fumes. Literally, its fuel supply is nearly exhausted. Its onboard battery, the backup power system that keeps it alive when the solar panels can't reach sunlight, has degraded significantly after 8 years of deep space operation. The battery's remaining capacity, approximately 1 hour and 40 minutes. The spacecraft is still functioning, still transmitting, still listening. And then it happens. Mangalayaan's orbital path carries it behind Mars directly into the planet's shadow. The Sun disappears. The solar panels, which have been drinking in sunlight for 8 years to keep everything alive, go dark. This is called an eclipse. For most spacecraft, it's a routine event. You dip into shadow, your battery carries you through, you emerge back into sunlight, and the solar panels take over again. But Mangalayaan's battery can handle 99 minutes of shadow. The eclipse lasts 7 hours. For the first 99 minutes, the battery holds. The spacecraft floats through the shadow of Mars, running on its own reserves, alone in the cold. Then the battery hits zero, the communication system shuts down, the temperature management system, which keeps the electronics from freezing or overheating, shuts down. The attitude control system, which keeps the solar panels pointed at the Sun, shuts down. When Mangalyaan emerges from behind Mars and back into sunlight, the panels no longer know which way the Sun is. The thrusters can't orient the spacecraft. The computer can't restart because it can't draw enough power. ISRO sends a signal. Nothing comes back. They send another. Nothing. They try again the next day, and the day after. They spend weeks sending signals into the silence, hoping for some fragment of a response, a carrier wave, a heartbeat, anything. April gives way to May, May to June, June to July, August, September. Every day, engineers at ISRO's Deep Space Network stations point their antennas at Mars and transmit commands to a spacecraft that can no longer hear them. On the 27th of September 2022, a final review meeting is held. The data is clear, Mangalyaan is gone. On the 3rd of October 2022, ISRO makes the official announcement. The mission is over. And Mangalyaan is still up there. Right now, as you read this, as you breathe, a dead spacecraft the size of a small car is circling Mars at 22,000 kilometers per hour. It will remain in that orbit for perhaps decades before Mars's gravity finally pulls it down and the thin atmosphere destroys what remains. Inside it, 5 instruments, 2 terabytes of data already transmitted, and whatever secrets it didn't manage to send back before the lights went out. Let's be honest about what Mangalyaan was. It was India's first attempt at interplanetary spaceflight, and by that standard, it did something extraordinary. It worked. Not just barely worked, it worked for 8 years, far beyond its planned 6-month mission. It produced a complete photographic atlas of Mars. It found puzzling atmospheric behavior that no one had seen before. It gave India's engineering community the experience, the confidence, and the institutional knowledge that would later make Chandrayaan-3's moon landing possible. The scientists who built Mangalyaan started, remember, from a church in Kerala and a bicycle on a beach. 50 years of learning. 500 crore less than NASA. And they reached Mars on the first try, something no other nation has ever managed. The gap between 27 papers and 500? That gap is real, and it matters. But it's worth understanding what creates it. NASA's planetary science program employs thousands of researchers. American universities have entire departments devoted to analyzing MAVEN data. The international scientific community treats NASA's raw data as a public resource to be mined by anyone with a question. India's planetary science community in 2014 was a fraction of that size. The ecosystem that transforms raw mission data into published science peer review, international collaboration, data sharing infrastructure was only beginning to develop. That it exists at all is remarkable. That it wasn't yet mature enough to extract full value from Mangalyaan's data is a fact, not a scandal. But